Hello, everyone, and thank you for joining our podcast this morning with Astron Drive. So, today we have some really exciting news to share with you. We did some major breakthrough in the warp drive research, and we got publication in one of the most reputable physics journals in the world. It is General Relativity and Gravitation. And during this podcast today, we're going to review what exactly we did, and we're going to try to explain why this is important. So my name is Ivailo Vasilev, and I'm the CEO of Astron Drive Technologies. And this morning we are joined by Nelson, as usual. He's the head of our warp drive research. So Nelson, please go ahead. It's your meeting now, and please help us to understand why this is important.
Thank you, Vailo. Hello, everyone. It's nice to be here again in a while. And yeah, we have excellent news. I have to say, this we kept this result for so long, and I was so excited. Now I'm so excited that we can share it with you openly, and this is great. So you see, the article addresses a real big problem, one of many that Word Drive already have, but this one's in particular, I think, is going to open a nice room for discussions and open a lot of new ways, maybe, of thinking about the problem. So if you see the title basically says what is in the article. The title says it is the influence of anisotropic matter. So as we discussed many times before, we wanted to complicate the warp drive approaches that were already there in the published. And the point of that is it's not always true that if you have a more complex matter distributions or configurations, your problem is going to be more complicated. And in this case, it turns out to be something in like that direction, right? So let me lead you through this more or less briefly. You can see what we did here is basically that we have the Alcubierre warp drive. I mean, is this the basic Alcubierre metrics where beta is the function that, in the case of Alcubierre's, it comprises the Alcubierre's form function along with the dependence in time and in position, right?
Nelson, I apologize, but can you please go back to the introduction and let's maybe start with what exactly we did and why this is very important. Maybe from the title, because probably it's better idea to give some information to our audience about the background of this article, why this is important, and after that, certainly, let's review the Alcubierre metric.
Okay. Yeah. You're going to start again?
I mean, we can continue from the Alcubierre metric where we stopped, but please give a little bit background information to the people why the problem with the negative energy is important and what we did to be able to say that it was like one big mistake which was made 25 years ago. And after that, we can give all the technical details you started explaining.
Okay. Sure. So let's then review that what is the problem with negative energy. So trying to go to technical, the whole problem comes from the fact that when you have Alcubierre's metric, as he proposes in the 90s, is if you think of it as if you have a set of equations, and then you think of it as if you have just only dust there, which is basically energy density at the end of the day. Well, it turns out that the equations tells you, apparently, this was something that Alcubierre himself realized at the moment. They'll tell you that you are trapped with a problem where your energy density has to be always negative. And the point of that is because you basically are using one equation that is, we can call it, this is like the time component equation of the Einstein's equations. And in there, you can see very clearly that it's a negative sign there that is bothering everyone for the last 30 years, basically. So that's partially true. What we found is like the that's not entirely true in the sense of that this equation, this time component equation of Einstein's equations, is just one of the whole set of Einstein's equations that you find when you're working with Alcubierre's warp drive, for instance. So what happens here is like the questions that we asked was reading other articles is, well, but what about the other equations? The other equations also play an important role in the system. And as it turns out, the other equations constraints how are going to be, or which are going to be the values of many of the constants or really the functions in the system. They basically constrains if you're going to have dynamic or not, how it's going to be your dynamic. Everything is set by this set of equations all together. So what we found is very, it was somehow astonishing, which is like, why is it that it seems that even in formulations where you work with extrinsic curvature and so on, uh, people used to ignore the constraints that could arise from Einstein's equations as a whole. And it was, well, it's surprising. It is surprising, I have to say, because in other systems this is not the case. I mean, you always take into account the whole set of Einstein's equations. For instance, if you're working with Friedman, Robertson, Walker models, cosmological models, well, to find the right equations for the expansion, you need to use all the equations. So what happens when you use all the equations in this case? Well, what happens is like you realize that their constraints are very strong and very dramatic, and the results are very clear. I think we believe that it's like you find that the depending of the type of matter that you have there, with that I mean if you have just dust, or you have a perfect fluid, or you have a fluid with anisotropics, then if you have all of these conditions, is going to tell you a different story for the constraints that you have in the system. So basically we found that if you have dust alone or a perfect fluid with it is completely isotropic, your density energy is going to be always zero because it's constrained. The system constrains the density energy to be zero. So that basically leaves the problem of negative energy density outside of the discussion. It's not on the ground anymore, and it leaves you with a system that is pretty much simple to study in a sense. But this is telling us that it's just not consistent to tell you have the Alcubierre's warp drive along with this energy momentum tensor and say that it's going to be have something negative there. There is an inconsistency there. And that's, I think, the most powerful message from the article is this inconsistency there. So how to avoid this or how to put together something that is consistent? Well, just let's put together all the equations and see if we can find something, some conditions on the matter that can give us like a nice dependence of the uh, density energy with some pressures, for instance, or some other distribution. So what we found out was like if we use an isotropic matter in the system in a very specific way and very well known, way of writing this energy momentum tensor, you find out that the energy density of the system depends only of the anisotropic on the system. And that's amazing,
So
because what you find,
Nelson,
yeah.
let me just interrupt here just to summarize my understanding. So basically, what you're saying is that it was long believed that you have to have negative energy to build a functional warp drive, and it was believed since the very beginning, since 1994, I think, when Alcubierre published his first article. But what we uncovered is that this is not required. I mean, you don't have to have negative energy in order to build a functional warp drive. And even further, to the best of my understanding, you're saying that we found a way to control the amount of energy which is required to create a warp bubble. Is this correct?
We found that there is a relation. So in a sense, first, yes, you're right. Alcubierre realizes this from the very beginning. In his article, it's already there, the problem. And that's, as it turns out, it's not really a problem. It's not there,
Right.
the problem. So, but it is true also that it's not required that you can have negative, you need a negative energy, as we see with this view, but you can have it anyhow. You can have it, but this is also a next step in the discussion, which is what you have is like the density energy depends solely on the anisotropy of the system. So the anisotropy in the system could be negative. That's a matter of a relation between the pressures in the system. So it is true, you can have negative, but it is important to say that the negative sign comes from the sign of the anisotropy of the system. It does not come from some exotic matter configuration, which is another step in these discussions, that you can discuss this and say, whoa, but you can have a negative sign there. Yeah, that's true, but it's not related to some exotic instance of matter, like some effect, like Casimir effect. But instead, it suggests that it will depend only on the anisotropy of the system. That's a breakthrough there. Yeah, and of course we have control in principle. We have control on the pressure of the system. If you can figure out how to put everything together in a real life experiment, you have control on the pressures. You have control of the matter in principle. So yes, you can basically have some. You can say for sure, I can avoid negative energy densities here.
All right. So what you're saying is that the requirement for the negative energy is not intrinsic for the warp drives. It is something which is result of the anisotropy of the system. So we can create a warp bubble with negative energy, but we can create warp bubble with positive energy. But for sure, the negative energy is not the intrinsic requirement for the warp drive, right?
Yeah, it's because the negative sign is very different to say that you have a negative sign that comes from exotic matter, strange exotic matter. I say that is a negative sign that is in the equations because you have one pressure that is larger than the other. It's completely different, and so it is like that. Basically, what this seems to suggest is that you don't need any more exotic matter for warp drive. Now you can face another type of problems, sure, but this is a different issue. It's basically saying that you don't need to address not known physics to try to figure out a warp drive. Now you can do it with just regular matter.
All right. So to the best of my understanding, now you're saying that we're showing that we don't require to have exotic matter to build a warp drive. So we don't have to have unknown physics because we don't know how to create negative energy and negative matter. On the other hand, you're also saying that it seems that by looking at the equations we have for the anisotropies, it is possible to create a warp drive with the technologies and the understanding we currently have for the matter. We simply have to find the right matter configuration to be able to do that.
Yeah, in principle, yes, it is in principle. I think we believe, people in the community believe, and they know one of the greatest problems to address, to try to even think in building, approaching the construction of a war drive, is was the problem of negative energy, and yes, it is not there. Yeah, we might have another problems. I mean, we have to figure out exactly what happens now with the amount of energy and so on. But it is in principle possible, as it is shown here in this article.
Right. So we really want to put the warp drive in the realm of the possibilities. So in the next several months, we're going to be very carefully to design experiments we can do in actual lab, just to be able to understand what type of matter we have to put and what kind of conditions we have to recreate. But it's really exciting for me because this puts indeed the warp drive in the reality of the possibilities, because we don't need to have unknown physics or exotic or negative energy or like matter. We can actually build a warp drive with the technologies and with the understanding to the matter we currently have. We don't really know how at this point, but we're going to spend the next several months of understanding and designing the experiments we can do in the lab.
Yeah, and that's going to be very exciting.
True.
This is like a very first step here, a very exciting step, I have to say.
Yeah, because probably you guys have read in the internet that this person is saying, okay, I'll do this experiment to do a warp drive and I'll do this experiment. So it was happening in NASA. Sony White did a lot of experiments like that. But the warp bubble was never ever created because we think that it's not question of luck to do certain experiments and to have certain intent to be able to create warp bubble. We're taking very different approach. So first we want to make sure that the theory is right. And based on the theory, we're going to design very carefully experiments with which we hope to create a warp bubble. But the experiments are going to be result of a lot of work and R&D we're currently doing with the warp drives and Einstein equations. So this is going to be our approach. And we already have several labs which want to partner with us for this experiment. So this is super exciting.
Yeah, yeah. I have nothing to add there. It's very exciting there. Yeah, it's just to see. And there are a lot of things, theoretically speaking, that we can work from here, and we have to. But I think we will speak about this later when the time comes.
Yep.
So far, what we are saying here is, I think, it's already important for the World Drive community.
Yeah, and also just a little bit more information. We're currently preparing 2 more articles. One of them is almost accepted for publication. We have several things to discuss with the person checking the article and the mathematics, and we have another one which we're about to submit. So with these 2 articles, we're going to give you guys significantly more details and information how we want to approach the problem of building a realistic warp drive. I think you're going to be really interested and excited. We have some really important insights we got when studying the warp drives. But Nelson, thank you very much for this background information. I feel that it was important for our listeners to understand what was the intent and what is the essence of this discovery. And so if you want now, for the most scientific part of our audience, let's go through the equations and let's review what exactly we did.
Yeah. Let's do that briefly. I think we the message is there, and I believe that what I'm going to do now, and if you're okay with that, if you feel so, this is just going on some of the details to give the you people the feeling, at least, that where this is coming from. And as I was saying, this is the Alcubierre metric, basically, and this beta function, it has everything there. Alcubierre, he gives a specific form from this, but we're not giving a specific form. We leave it this like an open function, but this function is the main character and in the system. Basically, whatever thing happens with Einstein's equations is they are going to tell us the conditions of these functions, and these functions this basically will tell us, well, what's going on with this function, what's going on with the energy matter. So as it is, this equation A here that you can see is basically the problem that everybody knows about this Alcubierre's warp drive, which is basically this what we call 0, which is the time component, which is equals to the density energy. This is what you see here. Yeah, you calculate your thing there, and you find that everything in here is square, right? And there is a minus sign here. This can be written in terms of the beta that I just told you that there is in the metric in this way. So basically, that's the problem. Oh, I have a negative sign here, and everything else is positive or square. So yeah, this is question now is telling you you have problem, dude. You have problem. You're doomed to have density energy all the time. So that's true, and that's because you're using, again, I have to tell you, this 0 component here and the 0 component here, of course. But what happens when you have the all the full Einstein's equations? Well, we go in there. In this section, we write Einstein's equations. We propose this is explicit energy momentum tensor. We uh, also have anisotropies. Uh, and with that in mind, I'll show you. This is the set of equations,
Well,
basically.
Nelson, I have seen this equation so many times, but I still get headache when I see them like that.
Well, these are equations that we don't intend to solve, at least not now. So we are not solving for beta, which is what people might think we do. We're not doing that. What we figure out is this. You see, if you have, this is the full set of equations uh, with anisotropic matter. What do I mean by anisotropic matter? Well, I mean this. You have a pressure in the y direction and a different pressure in the z direction and a different pressure in the x direction. So you have pressures in all spatial directions, and they are all different. And you also have your sorry, your density energy here. And all the other parts of the equations, these are the parts that comes from the Einstein tensor. So, but what I want to show here is that uh, if you put all the pressures equals to 0, this equation is equal to 0, this is equals to 0, this is equals to 0, and so on, right? And this term here is not here. So, and this it's like, okay, we don't care. This all from the question 14 down is this all or 0. We kept this the first one, and we figured out what's going on here, and that's it. But no, the truth is like this telling us is 0 is telling you a lot. It's telling you what is the relation. For instance, let's take this equation, the 15 here. It's telling you there is a relation between the derivative, the square derivative of beta with respect to c, and the square derivative of beta with respect to y. You have now a constraint here. Well, that's the basic spirit, the idea here. If you take into account all the constraints that come from these equations, basically we have a lot of them, and you make this system consistent, what you find is like beta is constrained a lot, and this relation here, this relation here is always 0, unless you have an isotropy in the system. And that was what we showed basically. We showed that. Let me see if I can show you very quickly here. So you see here, guys, this is basically we took here the from the Einstein's equations, what are the relevant constraints, keeping the anisotropy, keeping the pressures different from 0. And this, you see, you find these constraints, and once you find these constraints, basically they tell you that you have these two conditions here. And it's basically telling you, oh, what we have here is like this sum here of the derivative of beta are really related by the Einstein's equations with the anisotropy of the system. And if the anisotropy is 0, because you don't have any pressure, so rho is equal 0. If the anisotropy is positive, well, you have a negative sign with something positive, and this anisotropy is negative, you remove the negative sign. So basically, that's the whole spirit of the work here is this. to get into this result, basically these two equations here, and and you find that okay, if that's the case, can we obtain again the result from Alcubierre? No, there is no way. What we found is like the energy density is always proportional to the anisotropy of the system. So because of Einstein's equations. So basically, I think that's the whole story behind this. It's not very complicated. In fact, it's not complicated at all. Follow this, but it is well astonishing that this is, it's amazing. Basically, that I don't know, people in the community didn't notice this before, but well, here it is, and I think this is basically what our contribution at this moment for the Alcubierre's World Drive. We have more things in the article, but because we figured it out that we wanted to see what happens if we use different coordinates that are on the hypersurface that we write in the ADM formulation. And we did it for cylindrical coordinates and for spherical coordinates. I don't think it's necessary to go over there right now, but we found very much the change of coordinates tells you a mathematically different story, but at the end you obtain the same results. You can have positive and you have negative, and it's always depending of the matter of the system and not of some squares of the beta's derivatives, that as in this equation here. I think this is enough just to give people the idea, and they can just look into the article and follow up what is next.
Yes, and to understand that the mathematics may look complicated, it's actually not. It's quite simple mathematics, just a lot of variables we have to understand. But if you guys have any questions, please do let us know in the comments. We'll be more than happy to interact and answer them.
Sure.
And Nelson, before we close for today, thank you very much for this background information. I think it was super useful. Is there anything else you want to say?
No. So for the moment, I think we are very excited about this. We're very excited about the whole thing. This article, we have a nice struggle with the community for this to be published, and we're going to publish more results. We're still working a lot on the spherical warp drive, which is we think is the easier way to get there, and we're very excited of the partnerships that you talk about that hopefully we're going to have very soon. So that's it, guys. If you have questions, you have comments, whatever, just you can find this article in the website, and please just let us know.
Excellent, Nelson. Thank you so much, and thank you to everybody who spent the time this morning to listen to this podcast. And having said that, if you want to support us, there is the website, Patreon link under the video in the description. And with that, we are off, and let me wish to all of you to have a very nice and successful day.